Hello everyone, and welcome to another installment of the Interstellar Probe Study webinar series. My name is James Vestandria, and I am the Deputy Study Manager for the Interstellar Probe Study. Thank you very much for tuning in to today's webinar. We have a wonderful panel presentation today on the extra-galactic background light, opening a window to early galaxy and star formation. And after the presentation, we will have a question and answer session. Before we start, I would like to outline the logistics of today's event. As a member of the audience, your audio and video are off. During the presentation, please submit your questions in the question and answer feature, and please indicate which panelist your question is for. You may also upvote questions. During the question and answer session, I will start with questions with the largest amount of upvotes and proceed down the list. Also, for more information about the Interstellar Probe Study and for information on future webinars, please visit the Interstellar Probe Study website. And now I'd like to introduce today's speakers. Casey Liss is an astronomer at the Johns Hopkins University Applied Physics Laboratory. He has over 37 years of experience in the fields of astronomy, astrophysics, detector physics and development, and remote sensing data analysis. His current research focuses on studying the formation and evolution of solar systems by studying dust, gas, asteroids, and comets orbiting the host star. He has been involved in many NASA missions, and most recently is a member of the New Horizons science team, a member of the science team on SphereX, which is the spectrophotometer for the history of the universe, Epoch of Reionization, and ICES Explorer, and is on the Spitzer Space Telescope Extended Science team. Asantha Cooray is a member of the physics faculty and is a Chancellor's Fellow at the University of California, Irvine. His research covers the development of observational tests related to galaxy formation and evolution, especially in the infrared wavelengths. He is a member of the ESA's Herschel Space Observatory Spire instrument team and has recently chaired the NASA Origin Space Telescope Concept Development Study for the 2020 Decadal Survey in Astronomy. Michael Zemkov is an assistant professor at the School of Physics and Astronomy and the Center for Detectors at the Rochester Institute of Technology. His research focuses on experimental astrophysics with an emphasis in developing instruments and data analysis methods to study cosmological observations. His recent research focuses on measuring the infrared and cosmic microwave background to study large-scale cosmic structure, the epoch of reionization, and star formation history. Michael has held many prestigious leadership positions throughout his career, including being a co-investigator for SphereX, a co-I for the tomographic ionized carbon mapping experiment TIME, and the PI for the Lyman Alpha Mapping Project LAMP. And now, Casey, the virtual floor is yours.
Thank you very much, James. So we can go to my first slide, please. Thank you. So I'm going to talk today, I'm going to set the table for today's two speakers, Asantha Cooray and Mike Zemkov. And I'm going to talk about the rich amount of astrophysics that the Interstellar Probe can do as it journeys from the planets out into the nearby galaxy. We're going to talk about one specific piece and kind of astrophysics, which is going to be probing the cosmic backgrounds. Next slide, please. So cosmic backgrounds is a very hefty term that encompasses the entire universe. So what do I mean by that? Well, here's a picture that we often show when we're talking about Interstellar Probe. It's going to journey out of the solar system from the planets that we know and love, out through the heliosheath and the heliopause, and into the nearby galaxy. The nearby galaxy where stars happen. And in this picture is very nice, and suddenly stars happen, but we don't really talk much more about that. Well, there's a lot of exciting things that can happen among those stars, and not just in our galaxy, but in the entire universe collection of stars. Next slide, please. So what are we going to encounter as we go out on this journey? So the first thing we're going to do is we're going to encounter the planets. We're going to definitely be doing a course correction of velocity pickup by Jupiter. We're hopefully going to maybe go by ice giants and some KBOs. So there's lots of science we're going to do with the planets. Next slide, please. While we're flying through the region of the planets, we're also going to be flying through this two debris disks in the solar system. The dust kicked up as asteroids and short period comets sublimate and grind against each other in the inner system, as you see on the left in the green and the red, and in the middle where Kuiper belt objects get sputtered and they occasionally collide with each other and grind. And there's an outer debris disk, and ISP is going to fly through both of those and image them in ways that have never been done before by mankind. And we know that these debris disks exist around other stars. So you see on the right panel there, there's 15 different stars, excuse me, showing debris disks, and they have dust and gas around these stars. So what does ours look like compared to theirs? Next slide, please. Once we get past the planets and through our dust debris disks, we're going to be flying through the edges of our heliosphere into the heliosheath and the heliopause. And we know, again, I'm showing you pictures around other stars that we see on the left of this image. We know that there are shocks and there are edges to their astrospheres. And we call ours a heliosphere because we're more colloquial and we live here. So we're going to fly through this to the very edge. Nobody has ever flown through this and actually with a suite of instruments, a purposely designed suite of instruments to study them like we're going to try and do. We're going to try and look at them in the infrared. We're going to try and measure dust as well. We're going to try and do what the Voyagers and New Horizons going to do and measure particles as well. So we're going to ask the question, which one of these astrospheres we see around other and boundaries around other stars, what does ours look like? Does ours look like a comet, as you see in the lower right? Or does it look like a bubble? Depends on how important the solar wind is versus the in-streaming interstellar material. We don't know. And we especially will know best when we fly through it and actually measure it as we fly through it. Next slide, please. So once we're past this heliosheath and this heliopause, we're out in what we call the very local interstellar medium. We're out in the galaxy. We're outside our little baby environment, our local solar environment. And we only can measure this so far by remote measurements. And we think it has lots of structure, as you see in this pretty picture. Those shaded blue regions are different clouds, we think. And we think we're on the edge of one. We've never gone there and actually tried to sample pieces of its dust or its gas. And this will be the first time we ever do it. And that's going to be fantastic. We're not only going to get it in situ, but we're also going to collect light photons from this region and be able to compare the two. Okay, but wait, let's go to the next slide, please. There's more. That's as far as we're actually going to sample out into the nearby galaxy, but we can still look out even farther, especially since once we're past the debris disk and we're past the heliosheath and the pause, we've suddenly come out of an obscuring foreground light. And we're going to be able to see the galaxy in all its beauty. We live in a galaxy of like 100 billion stars. We are 2/3 out from the center of it. There's plenty more to see in this galaxy. Next slide, please. And our galaxy, I think, is only one of 100 billion or so other galaxies. There's lots of light coming from them too. There's lots of things we can measure, especially once again, we're outside the enshrouding local cloud. So next slide, please. So if I think advance it until we get the, thank you. So what is the EBL, the extragalactic background light? It is the light that after you're finished looking at the local galactic light and the local stars and local stuff between the stars, it's what comes from all the other galaxies that have ever shown in the history of the universe. And this is a very quick picture here showing you that white little ball at the very left is the Big Bang explosion. And this is how, well, over time, things have changed in the universe. First, we have the remnant microwave background. Then after a while, after quite a long time, we call the dark ages, suddenly you start making hydrogen atoms and then you start condensing into the first stars and the first galaxies. And then finally you get to the present day. We don't exactly know exactly how that happened. There's lots of information in these, what we call the extragalactic background light backgrounds. And in the lower right, you see from our next speaker, Asantha Cooray, his best understanding of what the different backgrounds look like, coming from the CMB, which is from the Big Bang, or the optical, which is mainly coming from all the stars and galaxies that were shown, or the X-ray coming from things like black holes and AGNs, giant exactive parts of centers of galaxies. And we're going to try and look in the infrared and the optical and measure these accurately for the first time in mankind's history. Okay, so next slide, please. I've talked theory, I've showed you a lot of nice pictures. What does it look like in reality? Here's what an all-sky image in 25 microns, so the mid-infrared, looks like to IRAS and to Spitzer and to COBE. And what you see here is a lot of black, which is good. That's very faint. This is in the locality of the Earth. And if you were to try and look just in the black regions, not bad. You get a pretty good measure. But you also have to worry about the foregrounds. You can see that there's this giant Z, light blue, kind of lightning blue Z. That is the dust in our Zodiacal cloud, making it you're unable to look at the background through that. And there's also the galactic plane, which is very bright. There's yellow, green, red. And those are both foregrounds, which are very hard to understand from 1AU. Once we get ISP out into the galaxy, that light blue, electric blue, is going to disappear. And we'll be able to, and galaxy is going to be much better understood. And we're going to be able to really go to town on understanding what is the exact nature, or what, at least what do we measure for the extragalactic background light. And with that, hopefully I've set the table, and I will go hand it over to our next speaker. So Asantha?
Thanks, Casey, and thanks, James and Pontus, for inviting to talk about astrophysics from the sort of the vantage point of the outer solar system. So I'll continue with what Casey was talking about. Casey gave a good introduction. I'll expand on that and talk about the science case and even the level of like science objectives for the level of like an STM. Next slide, please. So to taking a step back, you can ask like somebody did back in like 1700s, like Henry Colbert asked the question, why is the night sky dark? He was wondering why, every pixel or every point on the sky isn't lighting up with stars and galaxies. I guess back then just stars. So we can phrase that. So now we understand why the sky is not dark because of the whole expansion and the universe is not static and things like that. But there's a 21st version of this, which is what we are trying to get a handle on. And that is to ask, what is the spectrum of the background light in the universe? So by spectrum, you can think about like having a light bulb in your room and you're wondering like, at what wavelengths exactly it's emitting. Is it a spectral line at a certain wavelength? Or is it distributed? Is it more like black body? Things like that. So we want to do this over the whole of the electromagnetic spectrum. And we want to connect that spectrum to processes happening in the universe that emit photons. Next slide, please. So Casey showed a version of this. So here again, all the way from gamma rays to the left to the radio on the right. This is the intensity of the background sky. So this removes the solar system. It removes we are this part accounting for the emission from galactic universe, and the thickness of these curves, is some indication of the uncertainty or challenges related to these measurements. So you can see the microwaves, has a thin blue line, and that's the 3 Kelvin CMB, the cosmic microwave background that was detected in 1960s. The whole story related to that. And then you can also see that that's really bright, right? In these units of nanowatts per meter squared per steradian, it's about 1,000. It's kind of easy to detect. You know that those photons. Nowadays we have cable, but if you have the broadcast radio, those photons even make that fuzzy white noise between TV channels, or or radio channels if you are listening to like AM. Now the challenge is to expand that kind of measurements to the other wavelengths. So we want to go to the optical and the infrared. Next slide, please. So here's a sort of a zoomed in version of that optical to the left and the sort of the cosmic infrared background to the right. These data points, they span a huge range. There are measurements attempts done by essentially trying to count the photons in maps. There are lower limits placed by taking like deep images of the night sky with like Hubble Space Telescope from space, or the ground-based like Keck telescopes and things like that, and just like counting galaxies. So those are like lower limits. But we still haven't quite converged on at the level of like the CMB, right? We haven't quite converged and measured this very well. So that's the challenge. Next slide, please. The challenge, as Casey said, is we are not trying to make this measurement from like an empty place somewhere out in the universe. We are measuring this from our galaxy, from our solar system. So this is the Derby. I think this must be like 24 micron or 12 micron Derby map. You can see horizontally, that's our galaxy. Those are stars and starlight and the interstellar medium of our galaxy lighting up. And then perpendicular to that, you can see the ecliptic plane on the top, and that bluish is the zodiacal light. That's the dust scattered light, the interplanetary dust in the solar system, micron-sized dust particles carrying sunlight, and that lights up. And that's a big background for these kind of measurements at like 1 AU. Next slide, please. So you can ask like, so why do you want to do this, right? The previous one. Yeah, thanks. So we can ask like, why do we want to do this, right? Why do we care, right? So in extra-galactic universe, cosmology, astrophysics, we make, all sorts of measurements to understand galaxy formation and evolution. We call the this, this is a rudimentary way to get sort of on galaxy formation and evolution too. So what's being plotted is that same sort of background intensity, and these curves are different models of like galaxy formation and evolution. So if you can imagine measuring this to like the level of like a few percent or even 10%, you can separate out models and improve your models, and you can use this as another anchor in your toolbox to constrain galaxy formation and evolution. So on the infrared, in the optical, we are directly seeing the nuclear synthesis from stars. That's the direct star emission. In the far infrared or the infrared background, that's the dust scattered light. That's the reprocessed light. So there's an interplay between the two peaks, the one on the left and the one on the right, between starlight and dust scattered light. And that's crucial to understand like the dust product, not just the star formation or star light production, but also like dust production and the distribution of dust in galaxies and throughout the universe. Next slide, please. So then we can keep pushing this, right? So galaxies don't just show up randomly. There's a process in the universe. Early on, the universe was essentially empty. Something happened and the universe became neutral. As it cooled down, at that where it became neutral is the sort of what we call the last scattering surface. That's what we see in our cosmic microwave background maps. And then as time goes on, right, much later on, from this sort of primordial soup of hydrogen and helium, and perhaps dark matter and regions where there's more dark matter, gas cools, and then first stars form, right? So we think these first stars formed out of like hydrogen and helium, so they probably have this like unique properties. They were very massive. These what we call them population 3 stars, and they only lasted for a short amount of time. But they produced a large amount of UV photons. And these UV photons then propagated through this neutral intergalactic medium and then ionized. They carved out like bubbles. That's what you see as the number 4 on end of dark ages. They carved out bubbles, and these ionized bubbles with more and more UV photons grew. And the universe essentially became fully ionized at some epoch. We think it's around ratio 6 or 8. That's about 600, 800 million years after the Big Bang, but we don't quite understand what exactly the process. Next slide, please. And in addition to like star formation, these high mass stars, there are maybe other things, right? So we know from like Sloan survey at ratio 6, there are a billion or tens of billion mass quasars, so massive black holes. So there must have been like seed black holes, so mini quasars early on, and they probably produce some ionization photons or some UV photons. So there we can, there may be some contribution those, and these population 3 stars, they maybe like 50, 60 million years after they formed, and these pair instability supernovae also produce, UV background that may have helped with the ionization. And then there are probably some exotic things. People talk about like decaying dark matter and stuff like that. So there's interesting physics associated with this epoch of, early star formation, the first generation of star formation, and what happened there that we still don't understand very well. Next slide, please. But we can sort of like take a step back and ask, like, can we figure out like what's the UV photon density, or what's the today these will show up in the optical 1 micron near infrared background because of redshifting. What is that density? So there's a simple calculation one can do, because we know the amount of baryons in the universe because we have very good constraint on the Big Bang nuclear synthesis, the production of light elements, and we have very good constraints on that baryon density from the cosmic microwave background by looking at those acoustic peaks in the CMB power spectrum. So one thing we can say is at minimum there has to be a 1 UV photon per baryon, right, per hydrogen atom. That process starts reionization. It's probably more than 1 because of, there's recombinations going on, like, once you ionize, there could be recombinations and you need to pump more photons, but at least that gives you a lower bound or a lower limit with an argument like this. So next slide, please. So if you turn that, around, you can calculate what kind of signature could there be in the sort of the, one few microns from reionization epoch, from like the first generation of stars, so mini quasars, so some process going on. And this is that calculation. So you can assume sort of a very fast, quick reionization or you can assume a process that's gradual, takes a lot of time. But either way, this signal you predict around 1 micron is at the level of like maybe, you know, 0.6 to 0.8 nanowatts per meter squared per steradian. And if you can sort of like kept an eye on the plots I was showing before, the total galaxy formation since then, like the total you know, epoch of formation, evolution throughout the universe is about 20, 30 nanowatts per meter squared per steradian. So this sort of spectral signature from reionization, you know, is at the level of like less than 10% or something like that. So it's just a challenging, but you know, it's still that we do expect a spectral signature from reionization in the infrared background. Next slide, please. So why interstellar probe, right? Why not improve from the ground, from Earth or whatever, 1 AU or nearby? So this roughly 2 curves. Those are all the galaxies, galaxy evolution integrated. And then the green one is our own galaxy. That's the interstellar medium. So you can see around like 7, 8, 10 micron. Those lines, those are the power lines. Those are the amorphous carbon emission lines. On top of that, in black, you can see 1 AU, 2 AU, 5 AU. That's the zodiacal light. So that's the dust scattered light. That's the dominant foreground. You can see at, you know, 1 AU from Earth orbit, you know, it's way out there. You know, it's a factor of 1,000 larger. This plot even cuts off, so you can't see the exact amplitude, but it's like factor of 1,000 kind of foreground removal problem. But if you can get out to like 5 AU, you can see it goes below red, right? So that's the idea. We want to travel out. These 1 AU, 2 AU, 5 AU curves are not precise, right? Because we only have few lines of sight with dust counters. Maybe New Horizons and before that Pioneer and things like that, but we have some understanding, and then that we think the dust is falling off, but we don't know what's exactly happening. Maybe perhaps beyond 510 AU, maybe just one line of sight from like New Horizon dust counter, but the idea is like we want to get out there, get a clean view, and you know, on top of that, remember like that's the 10 AU is 10 nanowatts per meter squared, whatever 20 out there plotted is the total from galaxies, but we are also looking for a spectral signature on top of this that's below 1. So it's really essential we get a handle on this dominant foreground. Next slide, please. So this is, I'm putting these 2 objectives to the level that we need for like an STM. So on the galaxy integrated emission, that's the dominant signal. That's like the 20 nanowatts per meter squared per steradian. That tells you about the fossil record of galaxy assembly and evolution, right? From first stars to the present. So it gives you an extra handle, as I said, it's an extra sort of a anchor in our galaxy formation models that we have to satisfy, just like things we already have, things like the Madao plot that tells something about the star formation rate density in the universe. Then we can write down a second one, which is slightly more challenging to detect. That's the spectral signature on top of that smooth curve. That's the reionization signature. And that can give us a handle on, you know, what were the first objects to light up the universe and when did they do it. And then, you know, that amplitude and that shape of that spectral signature says something about the duration of reionization, the UV photon production, and how that's related to, you know, our models of galaxy formation. Next slide, please. Here again, so this science, the extra-galactic banner radiation on the right are again those same back that shaded. It's kind of shaded. The lower bound is what I was talking about, but I shaded it to say like, you know, you could have more than like 1 photon per baryon. Maybe it's like a few if there's gas clumping and things like that. The cyano light blue curves are again the zodiacal light bit like 1, 3, 5, 10 AU. So you really want to get out there to make use of an opportunity like this to get to the deep levels. It's really challenging, you think, to do this from 1 AU. Next slide, please. So there's other science, right? So I'm not, you know, gonna go into a lot of details. As we are traveling, we can understand, you know, as I said, there's dust, but we don't understand the dust production beyond maybe like 510 AU. But, you know, we think there's a sort of constant level of dust coming in from like Kuiper belt objects. Maybe there's an isotropic dust coming in from the interstellar medium falling into the solar system. So there's physics, there's astronomy, astrophysics to be done out there with the same instrument or a modified instrument. And I think Andrew Pape is going to talk about some, so I'm not going to go into details about this. Next slide, please. There's a connection you could make in a lot of these measurements, which is sort of an exosody. So you want to understand the dust. So I talked about the signal, and I treated like the dust as like a foreground, like a nuisance. But that nuisance is really sort of a signal, which you can understand that too. So, and the connection there is really to understand sort of exoplanet searches, the exosody in other stars. And there are, even considerations. So thinking about like imaging, direct imaging, perhaps with like an interferometer, and do you want to place that interferometer out in the at like 10 AU, 5 AU distances, or 1 AU, that couples directly to the amount of dust in the solar system. So let me, I don't know if I have a lot of time, but let me move to the next slide, please. Yeah, so I think this is my last slide. This is my summary. So I captured in my talk, tried to summarize two key things. So there's the light production coming from nuclear synthesis in stars, and the rescattering of those photons by dust in galaxies, and that leaves sort of like a broad spectral signature in the optical to infrared background, and that's at the level of this 20 nanowatts per meter squared per steradian. The shape constraints the light production versus dust production in the universe. It is an anchor for our galaxy formation models. And then the second one is perhaps slightly more challenging, and that's to go after that additional spectral signature on top of that sort of the optical background that shows up as a sort of a, as a small bump that captures something about reaction. First light. So I do now Mike, who's going to talk about the instrument concept to make these measurements.
Thank you very much, Professor Cooray. And now for Professor Zemkov's talk.
Hi, everyone. Appreciate you guys showing up today. Zoom fatigue is a real thing, so it's nice that we have so many participants. So thanks, Asantha, for the review. That was a lot on the what and why. I think I'm going to spend the next 15 minutes telling you about the how. Next slide, please. So just to recap really quick, what Asantha just said, basically these infrared E-bill measurements are pretty challenging to make from Earth. These are summary plots that we just showed, but I wanted to highlight a couple things. The lower left plot showing the near infrared background, you can see the discrepancies between people doing sort of absolute photometric measurements, summing all the photons, and people who, for example, count galaxies are still in the optical and near infrared on the order of discrepant by factors like several. Going further out at longer wavelengths, beyond about 5 microns, there aren't very many points on this plot, out to maybe 100, 200 microns. The reason for that is it's really, really hard, damn near impossible to actually do a measurement out there. And so there's reasons for that, and the reasons were already discussed by Casey and Asantha, which has to do with the zodiacal light and the fact that the Earth is embedded in this dust cloud, and that dust cloud, because of its characteristic temperature, is really, really bright at those sort of mid-IR wavelengths, far IR wavelengths. Next slide, please. So what do we know about the interplanetary dust and sort of how bright it is? Unfortunately, at the moment, the answer is not a heck of a lot. You can see the plot on the left there is a summary of measurements from Pioneer, which is basically our best source of information, 40 years later or so, on what does that brightness do as a function of heliocentric distance out to about 5 AU, so sort of like Jupiter's orbit. And shown on top of that is models from Andrew Pape, who makes models of this interplanetary dust, showing that it does decrease, and you do get a serious advantage from going, out further. That advantage is wavelength dependent to a certain extent, as you can see on the lower right there. That's showing the spectrum as a function of distance as we go out. interestingly, it does drop sort of below the level of the galaxy light and even the extragalactic background by maybe 510 AU. Remains flat, so there's hope that we might learn something, and then drops again out to sort of 100 AU, as shown as the upper plot in the upper plot there. So the idea is that as we go out, this light should be decreasing. We don't know how it decreases, but it's a good guess that it does, and it might plateau due to Kuiper belt dust, but then go away completely. Next slide, please. Okay, so the remit of the group that I've been working with has been to think about how might we do this extragalactic background science and other science cases using a spectral imager from ISP. And we take a few things as sort of the input to that. One is, first, do no harm. We recognize that we're sort of piggybacking and want to try and have a minimal impact on things like operations so that our chances are increased of going along. We like to think that our science is kind of central and very tied into the kind of questions that ISP is asking. But that said, we do want to keep a small footprint. This payload will likely spin, if not all the time, then at least some of the time. So we'd like to come up with concepts that allow it to spin, at least at some rate. We expect that pointing ISP is going to be costly. It's likely not to have inertial mass systems to point. It's going to be pointed by thrusters, and that requires a gas tank, and that means you can run out of gas. We obviously have mass and power restrictions. We want to have as small a footprint as possible because the payload, the overall payload of ISP was likely not to be very large. And of course, data telemetry from the outer solar system is painful. Next slide, please. So this is sort of looking at, perhaps you might think of it as the right-hand side of the science traceability matrix. Once you've identified the questions, which Asantha sort of outlined, this is more how do you put requirements on what do you want to measure. I won't read this, you can read through it, but basically to summarize, we would like to do measurements sort of from the near all the way out to the far IR with sort of resolution of a handful up to tens spectrally. We would like not diffraction limited performance. We don't need quite that good, but certainly something of that sort of size. Basically, sensitivity requirement is something we can achieve with known technologies. We're not reinventing anything. These are sensitivities that are very realistic in realistic integration times with existing stuff. Shared survey requirements between all these different wavelengths. Well, we want a big survey. We want to look at least more than 100 square degrees in several patches. So we're talking about hundreds of square degrees to demonstrate that whatever signal we see that's extragalactic is isotropic, because it should be. The universe, as we know, is not different from place to place. But larger is better. We would do an all-sky survey if we could, but I'll say more on that later. The other part of this is you need a cryogenic instrument. All of these wavelengths require cooling. The longer wavelength you go, the more deep cooling is required. So that's another requirement we have. Next slide, please. We saw a lot of this material before, so I won't belabor it. I really just wanted to sort of motivate there's heritage here. I don't think we're really talking about reinventing anything particularly new here. There's no new technologies, or at least not many, that we would need to enable this. The gold standard still remains basically Kobe-Derby, which is this montage on the right. Casey went through sort of this breakdown of the S-shaped blue stuff being Zodiacal light, and then the galaxies left over after that. And the diffuse isotropic stuff left over at the end is the extragalactic background. So obviously this measurement's been done, and the issue is actually not the technology as much as the fact that the dust cloud we're in is bright and time varying and just really difficult to suppress by a factor of 100 or 1,000 or even 10,000 that we would need. So that's hopeful. That says we probably know how to do this. Next slide, please. So one kind of non-starter out of the gate with this cooling is to use an active cooler. Active coolers are power hungry, they are heavy, they are large, they're kind of just not the right thing for ISP. But we do know that things cool passively in space, and actually using passive cooling to get to cryogenic temperatures is a concept that's been around for a long time, at least 40 years. that's kind of reached a peak recently and become in vogue for larger missions, like the Spitzer Space Telescope had a warm mission that was entirely passively cooled. Planck had significant passive cooling. An upcoming MIDEX that some of us are involved with, Spherix, is going to be entirely passively cooled as well. And near Earth, just because of the insulation from the sun, and some of these instruments were actually situated near Earth, or will be, you're limited to about 40 Kelvin. That's as much as heat as you can realistically reject. But the heat rejection depends on the radiation environment you're in, so we could expect that as you get further from the sun, that lowest temperature can reduce. And I'll say a little bit more about that next. So this is a concept that, or this is a technique that is really enabling for doing a measurement from ISP. Next slide, please. So this is just a cartoon concept of what this instrument might end up looking like. It's a three optic telescope. You can see on the right a little ray trace of what it might look like. It would have sort of a 7-centimeter clear aperture, so not a very big telescope at all. The whole instrument would be sort of briefcase sized. You can see that the telescope would illuminate a beam splitter that would send the far infrared light to the right and the near infrared light straight through. And then we would have, a few focal plane or a couple focal planes there that would let us make images of the sky. And then we would use linear variable filter technologies, at least in the near infrared channels, to be able to disperse the light. And that whole thing would be wrapped up in a sort of umbrella-like thermal shader that would allow us to passively cool. Next slide, please. So these are rough specifications for those of you who like to keep score at home. The way we're talking about it to the ISP team at the moment is we have a baseline design where we would go from about 0.5, which is optical wavelengths, to about 15 microns, so deep into the mid-infrared, plus a far infrared mapper that would let us do some far infrared work in 4 or 6 bands. There is a near infrared only D-scope that would remove the need for any kind of active cooling at all and be entirely passive. We would lose the far infrared stuff if we did that. But it is nice because it's more tractable and a little less resource hungry. And the idea there with either one of these things is we can be doing interplanetary dust science on the way out. We can be doing extragalactic background science on the way out. And we can do any kind of flybys that people may want to image planets or KBOs or things like that. Next slide, please. So in terms of concept of operations, how would this thing have to look? Well, the passive cooling technique sort of imposes one major rule on you, which is you can't look back at the sun, at least not, closer than 100 AU or something like that, because you'll blow your thermal budget. So really this thing needs to be mounted either on the front or perhaps to the side of ISP and look out that way. And what that means is because we can never look back at the sun, we really only have 2 pi steradians, so half the sky available to us in the direction of the spacecraft outward velocity. We could accommodate pointing and spinning by having a compensation mirror inside the telescope that would decompensate a spin, at least to a certain spin rate. And we could tilt the whole package to kind of get that extra axis so we could point up and down along the ram direction of the telescope. The other sort of con-op consideration here is telemetry requirements. Basically, the cost of doing a full 2 pi survey with this instrument is a fixed cost. It takes about 316 hours to do that. The thing that isn't fixed is the telemetry rate. That gets worse as you go out. If you sum those two things together, that's the furthest left column in that table at the top there. Near Earth or even beyond Earth out to sort of Mars or Jupiter, the telemetry rates are pretty high, and we reckon that we could do a full survey and telemeter that in about half a month per. But as we go out, that rate drops. So at Saturn, we're basically doing a survey a month, and by 50 AU, we're doing a survey a year. That might be okay. Again, the survey time is pretty quick. It's the data telemetry that's costly. So what we can sort of do is snapshots at sort of discrete distances as we go out. Next slide, please. Okay, so in terms of what we can do, I'm showing on the upper right the cooling profile using a passive system, assuming basically the spacecraft cooling performs as New Horizons did. And then there's the shaders as the dashed line. And the upshot of all that is that we can very easily accommodate a 30 Kelvin near-infrared detector operating in this telescope without having to do anything special. And that starts even at 1 AU and goes all the way out to however far you care to name. The far infrared channel is a little bit more difficult. That would require active cooling. Such technologies exist. They're about TRL4 now. You can buy something that's sort of small, or not buy, you can make something that's smaller than a Coke can. It requires about half a watt of power and get your 3 milliwatts of cooling so you could have a far infrared channel. So we're hoping that we can accommodate that. So what that would let you be able to do is shown on the bottom there. Basically, this is showing the signal to noise ratio per spectral resolution element as we go out. And the colors in these plots are color coded as red is the interplanetary dust, green is the galaxy, and then blue is the extragalactic background that we're ultimately interested in. And we're going 1 micron, 10 microns in the middle, and 100 microns on the left. What you can see is your signal to noise ratio is always very high. We are really sort of not limited by, but we're really studying interplanetary dust out to about 10 AU, give or take. That's the primary science driver. Beyond that, what we're starting to do is map the galaxy and the extragalactic background. We'll have to be able to separate those two things, but we know how to do that. That's a known technology. So there's no problem there. And interestingly, because we will be doing these surveys sort of over and over again, there's kind of a diminishing returns to that. So one can say, well, what really we should be doing is operating the instrument until we don't learn anything more about how interplanetary dust drops off. That happens about at 70 AU. We start losing signal to noise ratio. We've done all of our extragalactic background science, and so this instrument is really useful because it's something that you can operate out to about 7 AU and then just turn off. And you could turn it on again if you wanted to do a flyby or something like that. But basically our prime science is happening very early in the mission when the data rates are high and maybe some of the heliophysics, really interesting stuff having to do with the heliopause hasn't started yet. So it's a nice cost benefit there. Next slide, please. Okay, so just to finish up, there's still open items. Obviously, this is just a concept and we haven't worked out all the bugs or proposed it yet or anything like that. So this is just a list of things we have to consider as we go forward. What's the spin rate of the ISP? That's something that really dictates the feasibility of this concept. Can we be mounted to avoid the sun? The real estate on the front of the spacecraft might be a bit valuable. So, we have to talk about how that might look. What are the real telemetry limitations? The calculations we've done assumed New Horizons, which is probably a good guess, but are there things we don't know, for example? And then stuff that we have to do sort of internally within the science team are things like optical and cryogenic designs. Can we do designs and identify any technology development that needs to happen now so that we can be ready for 2030? I just wanted to highlight in my explosion on the left, or sorry, the right there, that we talked about EBL today, but we can really do other science with this thing that we didn't have a chance to talk to you about. We can do interplanetary dust, we can study the galaxy, we can study ices within the galaxy, and even other things as well. And I hope that as this talk series continues in the future, we can have some speakers talk to those kind of science cases, because I think they really integrate why this spectral imager should fly on New Horizon or on ISP. So just to finish up, we have a killer science case, multiple science cases, and we have a way to do it. We think we have technologies, so let's go and do it. Thanks.
Thank you very much to all of our speakers. And now we're going to have our question and answer session. I don't see any questions at the moment, so attendees, please feel free to post your questions now. Okay, we just got a question in. So to all panelists, I get the impression that the zodiacal light is produced mostly within 5 AU. So in terms of measuring the EBL, would you prefer piggybacking on a Uranus or Neptune mission than Interstellar Probe? I can send this to Mike first, and then we can also go throughout the panelist list.
Well, yes. So this is not a new concept. People have been talking about doing this kind of thing for years. And in fact, there was an older proposal that some of us were on called Zebra that was going out to a mission to Saturn. The difficulty, in fact, is more political than technological, which is to say ISP has kind of greeted us with open arms and said, hey, tell us what we can do, what you can do, which has been nice. Sometimes these missions tend to be a little bit more closed and difficult, and it depends on, you know, political things, let's say. So yes, we would accept other rides, but ISP is very accommodating and will let us do things like EKB science that would be difficult to do otherwise because we'll be flying through it.
This is Casey. I'd like to add something to that. With EBL eyes, what the answer we just heard from Mike is correct. There is a lot of other things we can do, as Mike also mentioned, as Asantha and I have also talked about. If we want to image the debris disks of the dust that is orbiting around the sun, we want to do that at long wavelengths, at 100 microns out to 100 microns in order to get the contribution from the Kuiper belt, which has just been detected for the first time by New Horizons in the last few years. And we know it's there and we need to measure it. And in order to do that, we need to get out to hundreds of AU. We got a lot farther. So the EBL, yes, we could probably do that out to 5 to 10 AU and then we're done. But the other astrophysics we touched on very briefly, or actually looking for hot dust in the heliopause, what's happening at the boundary between our local heliosphere and the galaxy. Nobody's ever done that before, and it might help an awful lot if we haven't detected it from Earth. We may have to get right on top of it in order to detect it. So there are other reasons to take this instrument out much farther than 5 to 10 AU.
Thank you very much, Casey and Mike. Asantha, would you like to add anything?
No, I think Mike and Casey, they answered pretty much. Yeah.
Okay, great. Our next question is from Ralph McNutt, and he asks, have you looked in any detail about how this instrument would compare to, say, the New Horizons LISA instrument for supporting a flyby of a KBO or a dwarf planet? So I can give that one to Mike.
Good question. The answer is yes. This is similar to or better than LISA because it has a expanded wavelength coverage and could potentially offer the far infrared information if that's of value, and we're told that it is. You know, in terms of aperture size, so spatial resolution, it's quite similar. But in terms of spectral capability, I would say it's going to add a lot of new stuff, and it's going to add a lot of new things that have to do with how ICEs work that I'm not an expert in, but perhaps one day we'll have a talk about that.
And to add to that very quickly, it's also going to, the REX thermal maps we got from single scans, it will actually give you entire thermal maps. Wherever you get the LISA information, you'll get a temperature map as well from the longer wavelengths of the body.
Thank you very much. And the next question is for Michael, and it asks, is the lifetime for the cryo cooler a concern? Is it expected to operate only until Interstellar Probe escapes the inner heliosphere, about 70 AU?
Well, that's a great question. So this particular kind of cryo cooler is closed cycle. The testing they have done suggests that it would last years. I don't know about decades. But again, you know, that's a conversation about how long do you want this thing to be operable for. But because it's not expendable cryogens, it doesn't really have a fixed lifetime, except if it leaks a little bit, you might lose some, you know, helium slowly over time. But that kind of stuff actually is really not that limiting. It should last for many years.
Thanks, Mike. And the next question is from Kirby Runyon, where he says, I like the instantaneous field of view for the near IR, but what's the full telescope field of view for Mike as well?
Well, you know, because we have a situation where we are basically fixing the number of detectors and their pitch, that is their size, their physical size. The field of view is a trade with the spatial resolution. The numbers I'm kind of quoting at you The field of view would be degrees on the side.
Thank you very much, Mike. And I think that's about all the time we have for today. So thank you very much to all of our panelists, and thank you for attending today's webinar. The next webinar will be on Thursday, December 10th at noon Eastern Time on the interstellar dust grains, galactic messengers, where we'll have a panel presentation by Pontus Brandt, Burley Sturkin, and Bruce Strain. Please visit the Interstellar Probe Study website for more information about the study and to view information on future webinars and events, including the third Interstellar Probe Exploration Workshop. Also, please consider signing up for our listserv under the community involvement section of the website to make sure that you are getting the latest information on all the upcoming webinars and events. Thanks for joining us and have a wonderful day.